Hello everyone. So, um, posting this video because material science is a brand new event. There's quite a bit I do want to cover, and I do want to give a couple model examples for you guys to kind of base your PSETs on. But unfortunately, Vincent and I will not have the time to do that inside the actual classroom. So I'm just making these videos in advance so that way you guys have a model to work off of. So this is, I guess if I want to put an actual title, week one examples. And I've been told my handwriting is not the best. Hopefully we will bear through it. So week one examples. So the very first example, I don't know how much of an introduction I need to give. Um, Hopefully not much, and hopefully you guys see this. I'll post this and I'll check it, and hopefully nothing dies as I'm working through this. Um, I don't know how much more of an introduction I need to do, but it's all right. So the very first example will be on slide 9, so interionic potential energy, and the question reads, if I could just put a circle there, given Na plus, so sodium, has an atomic radius. I should really put ionic radius because it's Na plus, but it's all right. Radius of 0.095 nanometers, and the chloride ion has an atomic radius of 0.181 nanometers. Um, what is the force of attraction between the ions? I need to figure out a better system of doing this because like if I have to write out every single question, I think I might just die doing that. Anyways, yeah, so this is on slide 9, and this is directly just using the formula that we have. So the formula that we have to use is just F net. Oh, sorry, F attraction, I should already say that instead, is equivalent to negative Z1 times Z2 multiplied by E squared, and then that's going to be 4 pi epsilon naught A squared. All right, so this is the force of attraction equation that we introduced to you in class. It's so weird to say, oh, I introduced this to you in class when I did not yet. It's the wrong direction. Even though I did not introduce this to you in class yet because it's still the summer, but it's all right, whatever. Anyways, um, yeah, so then when it comes to this, let's just figure out some of our variables. So then the actual equation that we're dealing with is, well, the one equation I wrote over there. So let's just like define some of the variables so that we're not completely lost. So Z1, Z2 refers to the actual charges. So Z1 in this case is going to be +1. And this is because of the sodium ion. Z2, let me make this a little bit more obvious. So Z2 will be -1 because the chlorine ion. All right. The electron charge is 1.6 times 10 to the -19th coulombs. I thought I muted this. All right, now it should be muted. Is it? No, it's not. That is so annoying. It's not muted. I don't understand why. Oh, I can't go any lower than that. It's all right. So the electron charge is 1.60 times 10 to the -19 coulombs, and epsilon is 8.85 times 10 to the -12 coulombs per newtons times meters squared. All right, so this is the equation we're going to be working with. There's one more variable I do need to define. Let me erase this. Yeah. I'm making a video right now. It's not that serious, but what happened? You're making a video? Yeah. I have to disconnect the headphones from this. How do you? Okay. All right. Good. All right. Thank you. Wait, but they can see it. I thought you were screen recording. Yeah. It's all right. After edit. Maybe. Okay. Anyways, there's one more variable we need to define, and that is a. So we're going to define that right now. Oh, whoops. That's not what I wanted. That's not what I wanted. So a is basically going to be the sum of the atomic radii of Na plus and Cl minus. So then we're given that Na plus is 0.095 nanometers, plus the number for chlorine was 0.181 nanometers. So then that comes out, and I'm going to convert it to meters because the reason why I'm converting to meters is because if you look at this epsilon over here, we see that the unit over here is meters. So then it's better to keep everything within the same units. So even though we have the answer in nanometers, I will convert that to meters, which is just taking the answer that we get over here, which I believe should be 0.095 plus 0.181. That's going to be 0.276 nanometers. However, this turns into 2.76 times 10 to the negative 10th meters. All right, perfect. So now we have all of our variables. So now we're going to just basically plug and chug. So we have FA, and we have the formula over here. So I'm just going to start plugging in. So then the Z's is basically +1 and -1 for the charges, multiplied by 1.6 times 10 to the negative 19th coulombs for the electron charge, 4 pi multiplied by 8.85 times 10 to the negative 12th coulombs over Newton's meter squared, multiplied by 2.76 times 10 to the negative 10th meters. All right, so then if we basically work through that, I'm going to spare you the math, and we should get an answer of positive 3.02 times 10 to the negative 9th newtons. So this is our final answer. All right, perfect. Now on to the very next slide. If the attractive force all right, so then if the attractive force between magnesium plus, so Fa between Mg2 plus and S2 minus ions are at equilibrium. And it is at it is referring to the force of attraction, 1.49 times 10 to the negative 9th newtons. All right, so then we're given that. And A, we need to find what is the corresponding interionic distance. So remember, the interionic distance refers to the distance between the two nuclei of the magnesium and sulfur. And we're also trying to find if S2 minus has a radius of 0.84 nanometers, what is the ionic radius of Mg plus, or 2 plus, my bad. All right, so this is our question. And again, it's just taking the equation that we know for the force of attraction, which we know to be this, as we saw with the last example. So Z a squared -4, or sorry, that's not negative, 4 pi epsilon a squared. So we know the charges, Z1, Z2, that's just +2, -2. We know the electron charge, that's just a constant. Epsilon is another constant, and 4 pi is another constant. So what we're really interested in, and we also know the force of attraction, that's given to us. What we're really interested in is what is this A value, which is the interionic distance. So here is just a simple case of algebra. So what we'll do is that we have FA multiplied by 4 pi epsilon A squared is equivalent to negative Z1, Z2, E squared. And then I divide so that I get only alpha, or not, sorry, not alpha, A squared on this side. So now I have 4 pi epsilon FA, and I need to take the square root of it so that I can get A by itself. So I should get a final answer, or a final equation of negative Z1 times Z2 times E squared over 4 pi multiplied by epsilon multiplied by the force of attraction. So this is the formula I should really be working with in order to figure out what is my interionic distance. All right, so let's start plugging things in. So we know the charges to be +2, -2 because we're working with magnesium and sulfur. So that's where I'm getting the +2 and -2 from. And I also know the electron charge, which is a constant, so 1.6 times 10 to the -19 coulombs. This is going to be over 4 pi epsilon naught, which is 8.85 times 10 to the -12 coulombs over newtons times meters squared, which is another constant, multiplied by the force of attraction, which we are given as 1.49 times 10 to the -8 newtons. Let me just extend this for completion. So then if we were to put this into our calculator, we should have a final answer of 2.49 times 10 to the -10 meters. All right. So then that is our answer for part A, which is just asking for the interionic distance, which is just the value of A. And now on to part B. So let me just label this A over here. Going on to part B, well, the interionic distance is essentially the ionic radius of Mg2 plus the interionic distance, or the ionic radius of S2 minus. Well, we know what the, or yeah, well, we know what the interionic radius of S2 minus is, which we are given to be 0.184 nanometers. So then it's just a matter of plugging the things that we know to figure out what we don't know. And I'm going to convert this value into nanometers just to keep the units consistent, which is important. So then this 2.49 times 10 to the -10th meters becomes 0.249 nanometers. And I got this value by just dividing by 10 to the -9th. That's how you could go from meters to nanometers. Right. So then I have 0.249 nanometers for my interionic distance. We're trying to find the ionic radius of Mg2 plus 0.184 nanometers. And just subtract by 0.184 nanometers on both sides, we get a final answer of 0.065 nanometers. And it makes sense that it is significantly smaller because if you think about how ionic how the electron transfer works, the electrons are being transferred from the cation, which is typically found where you have the electrons in its own energy level, and that electron is being transferred over to the anion. So then essentially you're taking the final electron within the energy level of the cation, which makes it even smaller, and then transferring that electron in order to fill the octet of the of the anion. But then since you're adding more electrons, the electrons will then start to repulse each other because likes repulse likes. So then thus it makes the anion a lot larger. So then it makes sense that we get a very small number of 0.065 nanometers compared to 0.184 nanometers. All right, so that's part two. Oh, and another, yeah, so then another equation or another usage of the equation. So then this is going to be on Let me read it out. Yeah. So then this combines the equations on slide 8, which is the ionic force for ion pair, and the interionic potential energy equation that we have on slide 9. So then the question reads, the repulsion force between Na plus, which is an atomic radii of 0.095 nanometers, and chlorine ions, which has an atomic radii of 0.181 nanometers at equilibrium, which I'll just shorthand it as EQ, is negative 3.02 times 10 to the negative 9th nanometers. All right, so we're given that, and A, this is our first task. Find the value of B being the constant, which in the equation you'll see later, using the repulsive force. I'll just shorthand it as F equation. And for part B, the bonding energy. E minute. And we get to assume that N is equivalent to 9. So then let's just start with part A. So then for part A, we have, if you go on slide 8, we have the part within the yellow box that says attraction force, but then we're more interested in the repulsion force because we know the force of repulsion. So then that's the part we really need to work on or use. So then FR is equivalent to negative NB A N plus 1. So then if we plug in whatever we know so far, we know that the force of repulsion is equivalent to negative 3.02 times 10 to the negative 9th newtons. It's equivalent to, and we're given that N is equal to 9. So then that's going to be negative 9 multiplied by B. B is what we're trying to solve for. And that's going to be over, oh, whoops, what happened here? Anyways, the interionic distance, which is essentially adding 0.095 nanometers and 0.181 nanometers. And I'm going to be converting that into meters because the B value is a unit within Newton times meters raised to n plus 1. That's the unit of the B value. So then that's going to be 2.76 times 10 to the negative 10th meters raised over n plus 1, which is just going to be 10. So then if we solve for B here, we get a B value of 8.59 times 10 to the negative 106 newtons times meters raised to the 10th power. So that's our value. That's our final answer for B. Perfect. So then we have that, and now we go into part B. So then for part B, if you look at slide 10, sorry, not 10, 9, we have E net. And the reason why we can use this equation, because when it comes to E net, we are given the information when the ions are at equilibrium. And when the ions are at equilibrium with each other, that means we have achieved the minimum amount of energy because that's where the ions kind of settle down. Because whenever ions settle down in terms of bond length, they settle down at the minimum energy. So then we can use that equation to figure out the minimum amount of energy that we have. So we use this equation, which I'll rewrite. So Z1 times Z2 multiplied by E squared. That's going to be over 4 pi epsilon A plus B over AN. So then now I'm just going to start plugging things in. It's getting really tough. So the Z1 and Z2 will be plus 1 and negative 1 because of the ions being sodium and chlorine. Those are just the charges of those ions over there. multiplied by 1.6 times 10 to the negative 19th coulombs. That's the E value. Oh, squared. Multiplied by 4 pi times 8.85 times 10 to the negative 12 coulombs over Newton meters squared. That's the constant. Multiplied by the interionic distance, so 2.67 times 10 to the negative 10 meters. And plus, I want to go down to the next line because I'm skipping a little long. The B value, 8 point, tough, 8.59 times 10 to the negative 106 newtons times meters raised to the 10th power divided by the interionic distance raised to the 9th power because n is equal to 9. So then that's just going to be 2.76 times 10 to the negative 10th meters raised to the 9th power. All right. So then if you plug in the math over here, we get a final answer of negative 7.42 times 10 raised to the negative 14th joules. All right. So then there's that. Just making sure I got everything. Okay. Okay. Cut off over here. All right, so going on to slide 13. So then slide 13 is the one that has the mixed bonding. So then it's titled mixed bonding. So then it talks about ionic character, about how is an indicator of the bond strength, where the higher the ionic character, the stronger it is. So the question that we are given is to find the percent. This is a question 4, was it? I think. So find the percent ionic character for GAAS. And we're given that the electronegativity for Ga is 1.6 and the electronegativity for As, arsenic, is 2.0. All right. So then this just goes back to the actual equation for percent ionic character, which is percent ionic character, which I'll just abbreviate as IC, is equivalent to 1 minus E, the first electronegativity minus the second electronegativity. That's going to be all over 4, and that's going to be raised to the second power. Let me make that a little more obvious. Multiplied by 100%. All right, so then let's just start plugging things in. So now we have 1 minus E. Oh, that's negative, sorry. That should be raised to a negative exponent. That's going to be negative 1.6 minus 2.0. And it doesn't matter if you do 1.6 minus 2.0 or 2.0 minus 1.6 because that's going to be raised to a second power. So it doesn't matter what you do, it'll just become positive in the end. Divide by 4, multiplied by 100%. And if we plug this into our calculator, we should get a total or final value of 4%. So because we have an ionic character of 4%, obviously this bond is not going to be very strong because it has a very low ionic character. Ionic character being stronger than covalent, or ionic bonds being stronger than covalent bonds, then because the ionic character is super low, it's going to be a super weak bond and is likely going to be easy to break. All right, so then that's a very quick example, just bashing that one. All right, so then I think that's pretty much all the practice problems that we have for bonding. So now we're on to the practice problems for, what was it, for crystalline structures. So simple crystalline structures. So this is example 5. And the first example we're going to go over, if we go all the way to slide 20, which is the introduction of the body center cubic, though the question is about the face center cubic, so it should really be slide 19. I apologize for that one. So then the question is, prove the atomic packing factor, so APF, for FCC is 0.74. And I would put a star next to this one because a lot of the PSET that you guys will be receiving later has a lot of questions very similar to this. So if we go back to the original equation, the atomic packing factor is essentially the volume of the atoms. So volume of atoms in unit cell over the total unit cell volume, which I'll just abbreviate with V. And I'm just going to rewrite this as Vs over Vc. So Vs, whoops, is equivalent to, okay, so great. So then when it comes to the volume of the atoms, this is why it's important that we kind of establish the fact that we're working with a hard sphere model where we can assume that the spheres are touching and that they are, well, actually spheres. And that we can just basically use the equation for a volume of a sphere, which is 4 over 3 times pi times the radius raised to the third power, which is the volume we're going to be working with, multiplied by the amount of atoms we have. So then since this is an FCC, we have a total of 4 atoms. And each atom will have a volume of 4 over 3 multiplied by pi multiplied by r cubed, which is just the volume of a sphere. So then just to rewrite this so it's simpler, that's going to become 16 over 3 pi r cubed. And then when it comes to figuring out the VC, the volume of the unit cell, well, we know that the side length of an FCC, which I gave on the slides, is just 16 times R3 times the square root of 2. So then that means, oh, sorry, that's not the side length. That is the actual volume of an FCC. So that's the actual volume we're working with. So then if we go back to this atomic packing factor, we'll just take that ratio and just set it up as 16 over 3 times pi times r3 divided by 16 times r cubed. Oh, sorry, that's not root 3. That's supposed to be root 2. So then the R3s will cancel out. We don't have to worry about that. But now we have the numbers. So if we just put in the numbers, if you plug them into your calculator, you should get a value of 1.74 or something very close to that. So then that's how we verify the atomic packing factor for an FCC is indeed 0.74. And that is the maximum packing that you could really have within an FCC. If you have an atomic packing factor that's less than 0.74 for a certain element, that means you automatically know, oh, it has to be less than 0.74. Can't be anything more than that. What else is there? Mm, mm. Okay. Actually, before I move on, I do want to mention a couple things with the hexagonal closed packing. So then if you go all the way to slide 21, I do want to mention, and this is going to be super important on the PSET that you get. It's going to be the hardest question on that PSET, possibly oh, running out of time here. I guess after I finish this note, I'm gonna make a part 2 of this really shortly afterwards. So I just want to make this note here. For HCP, the hexagonal closed packing, there's a couple of things that you need to know when it comes to the hexagonal closed packing because they are super important and it will help a lot on the PSET. Specifically one question, which is just a proof. Well, I say just a proof. It is the hardest proof on the PSET, and it might pop up on the mock trial, so you might want to study it if I were you. Haven't decided yet fully, but it's going to be important. And when it comes to that, just a couple pointers. If I were to draw the hexagonal unit cell, over here, you see that inside the image we have atoms that kind of form the top, but there's also atoms on the bottom and the middle. So then these are the atoms in the middle, and then the atoms on the bottom are over here. The distance from the atoms inside the middle, so then it's not very clear on my iPad because I'm not the best drawer, but then if you look at the atom center, which is the image on the far right on slide 21, the hexagonal closed packing is a lot more obvious. The distance between the base and the middle atoms is exactly C/2. And the distance from that middle atom to the top base is also C/2. So then add these together, you get C. And then when it comes to the base, if I were to draw out the base over here, you see how each angle is exactly 6 degrees. And because of the way that we're assuming it's a hard sphere model, which means all these lines are equivalent, that means these sides are all equidistant to each other. That also means that these sides are also equidistant to each other, which means it's just a collection of, was it a total of 6 equilateral triangles just forming a hexagonal base. So what you can actually do is that you can kind of separate those two. So then hopefully, is there a different color I can use? There is. You can separate each one like this. So that you can chunk the base. So here's one base. Here's another base. And here's another base. You can chunk each base into 3 different parts. And then to find the area of one parallelogram and then just multiply by 3 because the other 3 parallelograms are the equivalent to each other to forget the total area of the base. And that's important, which you'll see why, because the reason why that's important is because the general strategy for proving the proof of y c over a is equivalent to 1.633 is because we basically take the idea that volume for a hexagonal prism is just the area of the base multiplied by the height. Wait, what? That's not right. Why are they doing that? You know what? I don't know why I. Anyways, but like either ways, both are true. I don't remember the specific context why I mentioned. Well, both are true. It's not like both of them are wrong. Both are true. I don't know why I mentioned this one though. I don't remember why I mentioned that one. I don't remember what I don't remember what I put on the P set, but either way, whatever the P set question was with the hexagonal one, I think it's like question 5. This concept is important. And so is this concept is also important for figuring out the value. All right, I'm gonna go make the part 2 right now because I have 5 minutes left. See you later.